Good morning, everyone. Welcome, all of you. Good morning, all. So, we are going to continue our discussion on name reaction and reagents. Yes, good morning, Suman. Okay, let's wait for your friends to join in. We have more sessions on Friday and Saturday. So, continuously, we are having 3 sessions in which we are going to discuss important topics. Yes, right? Please tell me if you can hear me properly. Yes, all right. So, yeah, we'll just start in a moment. Let everyone join, all of your friends. Okay. All right, guys. Very good morning, everyone. So, we are going to discuss important topics today. We are going to discuss some reagents, right? Some examples of the reagents. So, this session is name reaction plus reagent series. Okay. And till now, we have done name reactions only. So, today, what are we going to talk about? We are going to discuss some really good examples of osmium tetraoxide, and along with that we will also do name reactions, Woodward cis dihydroxylation and Prevost trans dihydroxylation, and similar reactions to those. Okay, so we are going to consider all of these, let's say osmium tetraoxide, KMNO4, and sodium periodate, right? All of these similar reagents we are going to consider that how they are reacting with the alkene. And similarly, guys, the name reactions which we will consider are also important for the reactions of alkenes only. Woodward cis dihydroxylation, they have been asked in your examination, and Prevost trans dihydroxylation. Yes, so all of these are important with respect to the reactions of alkenes. Okay, we are going to discuss this very important point. Yes, good morning once again, all of you. So let's start, guys. Now, before moving onwards, let me quickly inform you guys that a detailed batch is going on Unacademy, in which we are discussing all the important topics of inorganic chemistry, organic chemistry, both these topics by me, and physical chemistry by Nurul sir. Alright, it is a detailed batch course, and if you only want to join for practice, then you also have a practice course, Chemithon practice batch, which is only practice batch. And we have I have already completed organic reaction mechanism topic over here, and from today we are starting reactive intermediates. All right, and Kripa Sindhu sir is taking physical chemistry over here, so I'll be taking organic as well as inorganic chemistry in this batch, right? So when you are joining an academy plus, you are getting both of these courses, and you're also getting the mock test. All right, you're getting the mock test, you are getting the community, the practice that I share on community, right? Daily practice problem, DPPs, everything you are going to get in the plus, and along with the doubt clearing session. So basically, guys, the offer which was providing you 20% off on using the code Jagriti S Live, that is extended till 29th of July. So if you are interested in joining, you can do so before the offer expires. All right. Chalo. And from today also in the free classes, we are going to start. This is the battle of poles. We have completed carbohydrate, amino acid. All of these topics are completed, right? In the free classes, right? So what you have to do is today we are going to start with spectroscopy. Just visit my profile and register. Okay. And if not in my profile, you can just join the group, Telegram group, and I'll share the link over there only. Okay. So yes, absolutely, guys. Let's start our discussion. First of all, let's talk about an important reagent, osmium tetraoxide, OSO4. All right. Very important this is, and this is often used for dihydroxylation of the alkene. Yes, good morning, Priyanka, Komal, Ria, everyone, Suman. Very good morning, all of you. So, yes, what are some really good examples of this reagent we are going to discuss? So, first of all, what is the oxidation state of osmium over here? Can you tell me? What is the oxidation state of osmium in osmium tetraoxide molecule? This is how the structure is. Yes, right? Absolutely, it is plus 8. So it is plus 8 oxidation state, which means that the osmium is electron deficient. Yes, we cannot say it is very electron rich. It is electron deficient, we can say. So alkenes are supposed to be electron rich. An alkene and a simple alkene can, get dihydroxylated in such a way that it is attacking the reagent like this. Okay, what is it going to get? Let's say this is your simple alkene molecule. Now, after the dihydroxylation, after this cyclic concerted type mechanism, this is a concerted mechanism, all right. So, after this step, you are going to get the osmate ester. Now, what is the oxidation state of osmium in the second step? Yes, in the first it was plus 8. What about in the second one, guys? Yes, it is plus 6. Absolutely plus 6. So, what has just happened? The osmium tetraoxide got reduced to this OS plus 6, right? And what is it going to give you? It's going to give you the osmic acid, right? And after the hydrolysis, it's going to give you the osmic acid, which is OS like this, right? So H2OSO4. This is the osmic acid that you're getting. So osmic acid is having plus 6 oxidation state, isn't it? Right? So this plus 6 oxidation state is no more useful to us. Why? Because now it is not that electron deficient to pull the electrons from the alkene. So that is why it is not going to react with the alkene further. But are we going to use so much osmium tetraoxide equal to the number of alkene molecules? No. What we are going to do is we are going to recycle this. Yes. So yes, we are going to recycle this. How do we recycle this, guys? By adding some oxidant. उसको हम क्या बोलते हैं? Co-oxidant. Yeah, because osmium tetraoxide itself is an oxidizing agent. So whatever we add now to oxidize this is the co-oxidant. First, for example, most popularly used is NMO. What is NMO? N-methyl morpholine oxide. That is NMO. Secondly, you can use some perchlorate salt, for example, silver perchlorate, because perchlorate is itself in chlorine is itself in plus 7 oxidation state, right? So very important. You can use silver perchlorate or sodium perchlorate or barium perchlorate like this. All right. So you can use any of these co-oxidants, and it can once again be reoxidized like this, recycled into osmium tetraoxide. Okay. So this is the whole thing, guys, that we have to know about the osmium tetraoxide, how it is working, and what is the structure of NMO. That also you see. N-methyl morpholine oxide looks like this. N-methyl morpholine oxide in this way. Alright, so this oxygen is going to be transferred, and yes, it is once again oxidized. So this is it. This is the basic thing about the osmium tetraoxide, how it is going to be used. Right. Now we will see the reaction, the type of reaction it gives when you are taking it on an organic substrate. So first example, guys, let's look at this. Let's say you are having a molecule in this way, a simple cyclic alkene, but it is tetra substituted. So osmium tetraoxide in the presence of pyridine and N-methyl morpholine oxide, what is it going to do, guys? Is it going to give you this kind of a product? Both the methyls are above, and both the OH are below. Is it going to give you syn dihydroxylation? Yes or no? Yes, because the osmate ester can form from one side only. So it has to give us the syn product only. It cannot form the trans product, right? So osmium tetraoxide is used for the syn dihydroxylation. Now this was a very easy example. थोड़ा सा example मुश्किल करते हैं guys. Yes, let's see. Now what happens is when you look at this molecule, right, this is a trans alkene. So how is the syn hydroxylation going to look like? Once again, the same thing. So how is the syn dihydroxylation going to look like in this example? Yes, both the OH are going to be on the same side or on the opposite side. Yes, look at this. Where are the OH? Yes, Komal, absolutely they are going to be on the same side. So even though the alkene is a trans alkene, when you are saying syn dihydroxylation in this format only, where both the alkyl groups, these are trans to each other, right? You just have to put the OH on the same side. Okay. Although, the process is syn dihydroxylation, it does not mean that it's always going to give you cis product. Okay. So yeah, pay attention on this. The OH are transferred on the same side, but if I'm just writing this molecule over here in this way, one of the OH will be on this side, the other OH will become below. So yeah, this is basically a trans diol. So you are not getting a cis diol, but anyways, that doesn't matter because the process is delivering the OH on the same side. So this is correct. All right. Yes. Now we move onwards and we see a very beautiful example on stereochemistry. Yes, guys, very, very important. Whenever there is a question on stereochemistry and with reagents, it is a question of double importance because there are two topics involved. Stereochemistry is involved and reagents to hai hi. Okay, now see, look at this molecule. What do you think? How should it react? It is going to give you the diol, you know that. But where the diols are going to form? Above or below? Yes. Osmium tetraoxide, NMO, second step में hydrolysis. Yes, where are you supposed to get the diol? Methyl is above, and this methyl is going to hinder the formation of osmate ester above the plane. This osmate ester is bulky, right? So it is not going to form above the plane, it is going to form below the plane, right? So if the osmate ester forms below the plane, the hydroxide will also be below the plane. This is once again syn dihydroxylation. Yes means that both the OH are pointing below. This is equatorial, this is axial. Alright, because of the conformational analysis. Right? So, very, very important that this is stereoselectivity that we are talking about over here. Let's say we are also talking about regioselectivity in the molecule. Yes, so I have two alkenes in my molecule, right? And I'm providing the same reagent, osmium tetraoxide NMO, and second step hydrolysis. So where is the dihydroxide going to form? Yes. Where is it going to form, guys? First वाले पे. Yes, first वाले पे, absolutely. Above or below? That is also a question. Above or below? Because if I'm transferring OH on this side, where should it be transferred? Above or below? This bond is as it is. Yes, above actually, yes. So the attack should be exo, yes. In the Norbornene system, you are having exo and endo. So the OH are both going to be attached above in this way. Very good, all of you. So this is your major product. All right. Now, next example is when you are having one methyl, or this is just a directing group that once again asking you where the diols are going to end up. Yes, where is the diol going to be? Below. Absolutely. Both the OH are going to be below. Very good. All right. So these are different examples where you understand the stereoselectivity, the regioselectivity. All right. Now there's a very important question about the directing property of osmium tetraoxide. That is, if I'm, let's say, this is example number 6. If I'm, let's say, using an OH group over here, right? Osmium tetraoxide, NMO, and then hydrolysis. So if I'm using an OH group, what should happen, guys? Yes. Where is it going to give the dihydroxylation? Osmium tetraoxide, simple NMO. Above. See, that's the important thing. That osmium tetraoxide will give steric hindrance. It will give steric hindrance with the already existing OH. This is the major product. I'm not saying that you won't form the above product. वो भी बनेगा, but वो minor होगा. ये major है. Why is it major? Yes. No hydrogen bonding. Yes, hydrogen bonding क्यों नहीं है, guys? Because hydrogen bonding करने के लिए, let's say this is some alcoholic group, and let's say we want the osmium tetraoxide to do the hydrogen bonding. ऐसी होना चाहिए hydrogen bonding. Yes, in this way hydrogen bonding should take place. That is, the proton is attracted by the oxygen connected to osmium. Yes. But what happens is osmium तो +8 oxidation state में है. मतलब कि oxygen is giving all the electron. This osmium, it is taking away all the electron density from the oxygen. अब ये सारी electron density oxygen से ले लिया. So oxygen is not delta negative, right? It is no more delta negative, right? So it oxygen becomes delta positive. A positive charge cannot attract another positive charge. इसीलिए यहाँ hydrogen bonding नहीं होती है, right? But when we are providing any chelating agent, the one which works best in this scenario is osmium tetraoxide. NMO is a co-oxidant. यहाँ एक chelating agent हम use करते हैं TMEDA. Alright. So what is TMEDA? It is nothing but a amine. Tetramethyl ethylamine. Alright. Alright. So this is just your TMEDA molecule. What is it going to do? It is just going to behave like a complexing, it's just going to behave like a donor agent to osmium. कैसे donate करेगा देखो. Donates to osmium like this. Now, when there are nitrogen donor centers for osmium, then definitely the electron density is released more to these oxygens, right? एंड व्हेन द ऑक्सीजन आर हैविंग इलेक्ट्रॉन डेंसिटी, तब वो हाइड्रोजन बॉन्डिंग करेगा और तब जो है हमारा प्रोडक्ट, दिस इज गोइंग टू बी अ डायरेक्टेड product, right? You are going to have a directed product, that is the OH is the diol is going to form on the same side as the OH by the use of TMEDA. All right, this is your major product. All right. Yes. Yes, Nishant, good morning. So, so guys, osmium tetraoxide is an important reagent, and there are some selectivity and rules over here, selectivity examples over here, very very important. और ये भी बहुत ज़्यादा important है that it does not simply do hydrogen bonding. In the presence of TMEDA only, it can do the hydrogen bonding. Okay. Now let's also consider, guys, if I am taking the same reagent, osmium tetraoxide, with sodium periodate, क्या होगा फिर? And this combination, what is it called? Alright, it's known as Limix-Johnson reagent. बहुत popular है ये. Let's say we are doing simple dihydroxylation to the alkene. Yes, हमने alkene को dihydroxylation किया. Very well. What are you going to get? You are going to get the diol. Diol बन जाएगा. You are going to get the diol, isn't it? Alright, let's say there are OH over here. Then what will happen? The diol is going to further react with the periodate, sodium periodate, NaIO4. ये क्या करेगा? It's going to further react with the diol and it's going to give you the iodate ester, isn't it? Let's look at this, how it forms. Okay, ये देखो. Now these, if the attack is taking place like this, let's say both of the OH are attacking over here, the bonds open up. This OH attacking over here, bonds open up. So both of the double bond oxygen become OH and it has one double bond O and one O minus, like this. Okay, and this is going to further break. It is going to further break down, and what does it give, guys? ये देखो, ये bond ऐसे break होगा. It is going to give you two molecules of ketone. Yes, two molecules of ketone, and you have iO2 minus. Alright, you have iO2 minus over here. Now, this is very, very important that you started from the alkene and you are ending up with a ketone. It is just the same like ozonization, isn't it? जैसे ozonization reaction होता है guys, वैसा ही है ना, same. Right, what do you say? Yes, निशांत, 2 months plan में लूँ तो syllabus 2 months का complete होगा क्या? Alright, see, syllabus is always complete only. राइट, सिलेबस ऐसा नहीं है कि आपको जब ज्वाइन करोगे तब से स्टार्ट होगा. देर आर कोर्सेज जो चलते रहते हैं. इफ यू स्टार्ट इन द बिगिनिंग ऑफ द सेशन देन यू हैव टू स्टार्ट फ्रॉम द बेसिक. अभी सारे कोर्सेज रिकॉर्डेड है बिकॉज वी हैव कंप्लीटेड लॉट ऑफ टॉपिक्स. राइट नाउ प्रैक्टिस इज गोइंग ऑन. तो आप जितना देख सको 2 months के अंदर, दैट इज अप टू यू. यू कैन कंप्लीट द सिलेबस ऑल्सो, और मे बी कुछ टॉपिक्स रह भी सकते हैं. कांट से अबाउट दैट. दैट इज अप टू यू कि आप 2 months में कितना कंप्लीट कर पा रहे हो. ओके, यस yes, yes, recordings are available. Practice session recording, mock test, everything is available once you join the Plus. Alright, so yes guys, so we have understood the role of periodate over here. If let's say this combination is used, तो हमें समझ में आ जाएगा कि हमें बनाना क्या है. Okay, now the same thing, yes, one more important thing guys, देखो, for example, this is not given to you. For example, osmium tetraoxide or lead acetate दे दिया. Lead tetraacetate is given. Is it something different? Is this reagent something different or is it the same thing as used over here? Yes, same है ना? Same work as done by the sodium periodate. Then why are we using this? Sodium periodate, guys, ionic compound hai. It has to be used in the aqueous solvent. It has to be used in the aqueous solution. और lead tetraacetate क्या है? It can be soluble in organic compounds also. Organic solvent में ले सकते हैं. It is soluble in the organic solvent. Right? So it is the same thing. They are doing the same thing exactly, breaking the alkene into a ketone. Okay? Now let's look at the osmium tetraoxide one more time. This time doing a different thing. This time reacting with the alkyne. ठीक है? Osmium tetraoxide reaction with alkyne. Alright. So yes guys, before moving onwards, मैं आपको फिर से बता देती हूँ. Today is Thursday, tomorrow is Friday and Saturday. So Friday and Saturday we have YouTube sessions. What are we going to discuss? Name reactions भी करेंगे and we are going to study the use of metachlorobenzoic acid for epoxidation and other epoxidizing agents. So it is very, very important you attend these sessions, right? We have like these are some really important reagents, right? Chalo. So osmium tetraoxide reaction with alkyne. Let's see this, right? So this is your alkyne, for example. Definitely, I'm writing the same thing in one step. Lekin osmium tetraoxide reacts twice with the alkyne to give you this kind of a molecule because there's double electron density over here. So it's going to react from this side and it's also going to react from this side. Okay, what does it give you? Sorry, this bond should be over here. Alright, like this. Okay, so this is what you have, one oxygen at the center. This is what you have. Now the whole molecule is going to break down. But how does it break down? You're not going to break the carbon-carbon bond. Alright, that's not going to happen. The molecule is going to break in such a way that you get a diketone. Right? So let's say इस bond को हमने यहाँ transfer कर दिया. Alright, then what will happen? This bond should open up and go to the osmium. Similarly, this bond opens up over here और ये bond निकल के osmium के पास चला जाएगा. So ultimately, what do you have? You have a diketone in this way. Alright. So reaction of an alkyne gives you a alpha diketone molecule. Alright. Alpha diketone molecule is provided by the reaction of an alkyne with osmium tetraoxide. Alright, so we have seen plenty of examples of osmium tetraoxide. We have seen कि कैसे ये react करता है, everything. Now we are quickly going to compare this to potassium permanganate also, doing the similar reaction. Yes guys, you have seen sin dihydroxylation with potassium permanganate also. Yes or no? चलो फिर let's compare KMNO4, potassium permanganate. Now potassium permanganate is only going to give dihydroxylation when it is used with a base in the basic medium, right? तो ये क्या लिखना है हमें? Always remember KMnO4 along with OH minus. This is going to give you syn dihydroxylation. Yes. All right. So what is the oxidation state of this manganese over here? What is the oxidation state of manganese? Is it +7? +7, absolutely, in the highest oxidation state. Yes. So potassium permanganate in the +7 oxidation state is used for syn dihydroxylation only in the presence of a base. ठीक है, देखो क्या होता है guys. Let's say you are having this molecule. Let's say you are having this molecule. What is going to happen? Once again, this molecule is going to give you a manganate ester. जैसे हमने osmate ester बनाया था. Similarly, see, KMnO4 is not simply taken because it's ionic. तो हम क्या लेते हैं इसके साथ में? हम लेते हैं 18 crown 6. You are often going to see either 18 crown 6 being used or some other phase transfer catalyst. What is this phase transfer catalyst going to do? ये क्या करता है guys? It captures the yes. Alright, just a second. Yes, it captures the potassium in this way, and since it has a hydrophobic outside part, see, because of these ethyl rings, the outside part is hydrophobic. तो ये क्या है? अब ये KMnO4 को ना, it is going to carry KMnO4 into the solution, into the organic phase, right? So this is the phase transfer catalyst which is importantly used in the KMnO4 to bring the MnO4 minus, the manganate ion, into the organic solvent. Once it does so, you are going to have this kind of a ester formation. Now obviously guys, which is the less hindered side, above or below? Which is the less hindered side according to you? Yes, absolutely guys. Above side is the less hindered side because there is only one carbon for steric hindrance. Below side mein there are two carbons for steric hindrance. So it is going to form above या फिर exoester formation. Alright, so that is why when you are doing the dihydroxylation, you are going to get the exodiol in this way. OH and OH, both of these are above. You are going to get the exodiol. Alright. Yeah, so this is the major product. Is it same like the osmium tetraoxide, the stereochemistry? Is it the same? क्योंकि osmium tetraoxide में भी यही होता है guys, forms above. Yes, right, it also forms above. So the same thing is happening over here. Yes. So when you are doing this reaction in the presence of a base KMnO4 minus, in the presence of a base you get this molecule. अगर मैंने same reaction कराया होता, KMnO4 in the neutral medium, what would you get? You would break the molecule down and you will get CHO on both the sides. ये product बनता है if you are doing this reaction in the neutral or the acidic condition. Alright, so very important. KMnO4 in the presence of a base gives you this reaction. Alright, so we are only considering potassium permanganate for the dihydroxylation. There are very important reactions that we need to consider from the alkene point of view for one more possibility of syn dihydroxylation guys. ये देखो चलो, this is done. KMnO4. One more important possibility is Woodward cis dihydroxylation. Woodward cis dihydroxylation. Yes, very important, isn't it? ये देखो, what is happening? You are having an alkene, let's say. This is R and this is also R, for example. In the presence of iodine, silver acetate, acetic acid, and water, you are going to get you are going to get the OH on both the sides like this. Alright, what does that mean? You are getting the syndiol once again. Both the hydrogens are below. Does it make sense? Yes or no? Whatever I have written. Woodward cis dihydroxylation we have studied before also. We are just going to quickly see the mechanism of this reaction now. Yes, understood. Okay. So how does the mechanism go, guys? Let's see. आप खुद से भी लिख सकते हो. Tell me what is the first step. First step is iodonium ion formation. Yes, इस तरीके से iodonium ion formation. Right? What is the second step? Second step is you are having silver. Silver plus attracting the iodine, and this OAC, sorry, this is going to be OAC minus, right? Let's say कि iodonium ion above से form हुआ है. Let's say the iodonium ion has formed above because there are two hydrogens. You have to take those also into consideration. So let's say iodonium ion above से form हुआ है. Okay. So this acetate is going to attack from below. Yes, in this way, the acetate is going to attack from below. So basically, if there is inversion, the inversion is going to take place like this. या फिर मैं यहाँ पे ये लिख दूँ acetate OAC over here. All right, the R goes above and the hydrogen is as it is but shifted above. Right, that also makes sense. This also makes sense, isn't it? Right. Now, what is this acetate going to do? The acetate will do NGP. The acetate will do NGP in such a way that the iodine is going to go away with silver plus, right? ये ऐसे कैसे आ जाएगा देखो. The acetate is doing NGP in this case, right? So this product, this intermediate is common in both the Woodward cis dihydroxylation and Prevost trans dihydroxylation. ठीक है, बहुत important है. This intermediate is common in both the reaction. What happens is in the presence of water, when water is present, in the presence of water, water is going to attack on this carbon. Water is going to attack on this carbon. And the bond opens up, right? Which means water is hydrolyzing the carbon, the acetate carbon, right? And after the hydrolysis, you see at one side, alright, this is a proton. At one side, you have the bond is going to open up. At one side, you are having a OH, and the other side, you are having a acetate. This is what you see. First of all, in the first step of hydrolysis, right? One of the bond breaks and the other one is an acetate, absolutely. After complete hydrolysis, we are going to get the syndiol. Yes. So does it make sense, guys? What are we doing? बहुत ही simple सा reaction है Woodward cis dihydroxylation. That is, if you are taking a trans alkene, जैसे कि मैंने cis alkene से start किया. If you are getting a cis alkene, what do you get? You get a meso molecule because the diol formation is also cis. If you are taking a trans alkene, what would you get? Diol या फिर you're getting the mesodiol या फिर DL pair. Yes guys, trans alkene पे अगर लेंगे ये वाली same चीज in addition on the trans alkene, you will get the DL pair. That is, you are going to get two enantiomers. Okay, just try to draw them. Very very important. This is dynamic stereochemistry में आता है. If you are having a cis alkene and you are doing the syn addition to it, this is also syn addition, right? ये देखो syn diol formation. So if you are doing so, you are going to get a meso molecule. If you are taking the trans alkene and you are doing the syn addition, you will get a DL pair. Okay, very very important. Yes, absolutely. Now let's also look at the Prevost trans dihydroxylation. All right, let's also look at the Prevost trans dihydroxylation. So basically guys, I told you कि everything is the same. Yes, let's see over here. Okay, so this is the same alkene, let's say. This is the same alkene I have taken, and I am providing iodine, silver acetate, but this time you are only having silver acetate or some other acetate or benzoate like that. Okay, it's not necessary that you have the acetate only, you can have benzoate also, just any carboxylate anion. But only in the presence of organic solvent. You are not taking water over here. There is no water. So if there is no water, first step guys, at least this part is going to be the same, isn't it? ये तो ऐसे के ऐसे रहेगा. That is iodine addition followed by acetate attack. Yes, acetate is doing NGP. So this part is the same, isn't it? In the trans dihydroxylation also. Yes, ये same है. तो इसी को लिखेंगे as it is. As it is, we are going to write this. Let's say both the R are above now. Both the hydrogens are below. Okay, in this way. So this also looks like ये तो sin है. इसको तो sin product मिलना चाहिए. But no, what happens is the major step in this reaction is that once you have formed this intermediate, the acetate is doing the NGP, no problem. But after that what happens? क्योंकि water नहीं है. Since there is no water, water होता तो यहाँ attack करता, right? But since there is no water, the acetate is going to give you attack on any one of these carbons. And what does happen? ये देखो, as it is inversion on this carbon. So the R group is going to go above. Hydrogen is like this. ये पूरा inversion हो गया है. And this bond opens up. You are getting another acetate. So what is this now? Is it trans? इसको rotate करके लिखो. Rotate this. Let's say I'm writing both of the acetates on this side. This carbon is as it is. Okay. Yes. So you now see that if we are keeping the acetates constant, we are having both the R group on the opposite side, which means after the hydrolysis, H3O plus. Yes. After the hydrolysis, it is going to become like this. OH, OH, right? One R group is above, another R group is below. So it is the same representation guys. अगर आप ऐसे लिखो तो भी एक ही बात है, और अगर आप ऐसे लिखो one OH above, one OH below, ये भी same ही चीज है. Both of these are same. Alright, same molecules. Okay. So one very important thing, in the cis molecule, when you are doing the previous trans dihydroxylation, you get the DL pair. Yes or no? You get the DL pair when you are starting from cis. अगर मैं बोलूं कि मैं trans से start कर रही हूँ, trans alkene, yes. If we are starting from the trans alkene, what would you get as the product? DL pair बनेगा. Trans alkene के ऊपर anti addition, trans alkene पे anti addition, yes. So both of this is cancelling out. You are going to get the meso molecule. Try this out guys. It is very very simple. You are just going to get the meso molecule, right? Yes, yes, absolutely, meso molecule. Okay. Very important reaction with respect to the alkene system. All right. So guys, we have done the reagent osmium tetraoxide. We have seen. मैंने आपको बताया था कि हम ये सारी चीजें देखेंगे, वो हमने कर ली है. And in the next session, as I have told you, we will be starting from epoxidation. All right. In the next session, we will be starting from epoxidation. When is the next session? Next session is Friday and Saturday. All right. Two more sessions are remaining. We are going to start epoxidation over there. And there are other examples. There are other very important reactions that we are going to do. Yes, subscription related contact करना हो तो कैसे करें? Yes, Nishant, you can message me on Telegram. आप ये group भी join कर सकते हो Telegram पे. This is the Telegram group CSIR NET 2022. All right, and you can message me personally also on Telegram. Okay. All right. Yes. And very importantly, guys, अभी देखो today 5 p.m. Sorry 6 p.m. Today 6 p.m. we are having another battle of polls session, and that session will be on spectroscopy. मैंने आपको बार बार inform कर दिया है already. Spectroscopy पे free session है, practice session है. So what you have to do is you have to revise all the previous topics. Start from UV visible. Okay, we are going to discuss questions of UV visible today. And from tomorrow and next battle of pole session, we will go on doing infrared and NMR and ESR and MOSBR, all of those, mass spectroscopy and everything. ठीक है, पहले start होगा UV visible से. Okay. So guys, I want your advice on what do you want me to do in the month of August, right? So August के लिए, what do you want me to do on YouTube? I need your advice on this. Do you want me to continue the name reaction series? Do you want me to solve previous year questions? Or you want strategy sessions? What do you want? Tell me in the live chat. I'm waiting. Yes. Because previous year questions we are discussing in the battle of polls. Short topic revision, Komal. Okay, what short topic you are having in your mind? Previous year question practice, name reactions और reagents revise करा दो. Yes रिया, वो चल रहे हैं. Reagents remaining है, name reaction बीच बीच में हम ले लेंगे थोड़े बहुत. Should we continue the same series? All right. Question practice. See, Deepam, are you not attending the Battle of Polls? Here we are doing free question practice daily. Okay. चलो ठीक है. Like Orgel diagram. ठीक है. Questions भी साथ में. अच्छा ठीक है. Okay, we will do that. So whatever we are doing revision plus practice. ठीक है. Next month के लिए फिर हम ये रखते हैं revision and practice. All right. Watching recorded. अच्छा, no problem. Okay, Deepak. Deepam, sorry. All right then. Okay. चलो ठीक है. We will try to do that revision and practice for the important topics. Right. This is what we will do on the YouTube of the next month for the month of August. Right. The timing will be the same, Friday and Saturday morning. Okay. Chalo. So, all right, guys. Now I will see you all at 10:30 a.m. We are going to continue our discussion on coordination chemistry. Right. We'll see you very soon. Bye, everyone. Bye, guys.